Good evening. This is Joe Fields with week 6 assignment for FTT 122, Introduction into Ammunition and Basic Ballistics with Andrew Deering. This is Joe Fields. Tonight we'll be going over week 6, which is seven different items that we're going to try to explain with everyday items. For this project, I'm going to do a couple of different cuts to get to places to kind of use everyday items to explain some of these theories. Some of these I'll explain with things I've got around me right now. The first item that we're going to go over is trajectory. Trajectory is the path of any object through time and space. It's a very broad definition, but trajectory in the firearm world means it's the path that a bullet will take once it leaves the firearm. Gravity, air, humidity, all environmental factors, as well as propellant and the type of ballistic coefficient that the round has will affect trajectory. But at the end of the day, gravity and wind are the two biggest things that really kind of play an effect onto it. To explain trajectory, I am going to take a snap cap bullet, and I am going to take my camera and flip. Snap cap, thrown. That is trajectory. That was the path that object took to get to where it needed to be. Sights. Sights are any mechanical advantage on a firearm that allow you to align the front of the barrel with the rear of the firearm to establish a proper trajectory to get to the target you're looking for. The easiest way for me to explain this with everyday items is how I explain it to friends. 2, 1. That is your typical sight group on most firearms that have iron sights. This is your front pin. These are your back pins. You want to line these up and get them all in a nice little friendly line. Really, sights are any type of device that allow you to align the firearm with the target. That's the easiest way that I can explain it. Gyroscopic drift is the next item. Gyroscopic drift is the spin of an object as created by the twist of a barrel. Gyroscopic drift can apply to other things also. You might see it in regards to a soccer ball being kicked and have that little kind of wanky move that it makes through the air. You see it with golf balls, people playing a slice or a hook. You see it in curveballs and baseball. There's a lot of different things with gyroscopic drift that you can kind of apply to here. Footballs is going to be my preferred example of this. You're going to see a football naturally move the way that the spiral is applied. So the more spiral applied to the football, the better basically ballistic coefficient that the football has because of the spin to the object. But that ball will tend to spin the direction of will tend to move the direction of the spin. So that's the best way I can kind of explain gyroscopic drift. Drag. How can I do this one? Let me go get my snap cap. Hold on. Snap cap, air, coffee. Now I gotta get a new coffee. Drag on the projectile before hitting the denser coffee material was less. It moved faster through less dense material, which would be the air. Moved slower through more dense material, which would be the coffee. That's the best way I can explain drag. The Magnus effect. These effects are a little bit more detailed. The Magnus effect has to do with spin and airflow, how it curves through the air. The best way that I can kind of explain this would be air pressure differences. You see some of this in aerodynamics with airplanes. We'll go this way. And we can blow over the top of this. Let's see if I can do this right. You can see as I blow over the top of the toilet paper that it rises. Because the movement of air, the pressure of the air over the top lifts as opposed to the lower pressure on the underside of the object. That same principle applies to anything that moves through air or a fluid, anything. Choreo, easiest way I can demonstrate this. Spinning clockwise, because we are in North America. It's the effects of the rotation of the Earth on the fluid dynamics of what you are traveling through. It's more difficult with some of these global effects to demonstrate them and to... I'm not going to drink that. It has my snap cap in it. How to explain them, but basically it places an effect depending on the hemisphere of the Earth that you're in on the type of movement that your projectile makes through its trajectory. The Items effect, which I was completely unfamiliar with, is the principle that the Earth is moving, and your target, depending on whether or not it's east or west, is going to be higher or lower in comparison to trajectory as the opposite. So a target moving from west to east is going to naturally start increasing in height, whereas east to west is going to start decreasing as it moves around the backside of the circumference of the Earth. It's only used in long distance stuff. And even then, it's not as great of an effect as what you would see with gravity and wind. It does play an effect, but not as much, I think, as all others. The best way to explain the effect would be, I guess, a merry-go-round or a lazy Susan. Where if you spin the object and you try to roll a marble or something towards the target that you're picking at the time while it's stationary, you spin it, you throw a marble at it, and you try to hit the same target. The target you aimed at while it was stationary or at the time of the spin that you sent the object is not going to be in the same place as when your projectile or marble hits the intended target. It's difficult to show with everyday objects. What I would probably do if I could, I'd take a record player, turn it on, throw a marble on it, and watch how the spin deflects the initial target that you were aiming at. Vertical angles is... It's really it's a mix of thinking and overthinking the shots. If an angle that you're aiming down at in your head, you want to aim lower because you assume that it's going to drop faster and get to Earth quicker. Reverse with higher elevation vertical angles is that you would think that gravity is going to pull on that for longer. When in actuality, those vertical angles are tricks. You aim, if anything, low. On both high and low vertical angles to hit dead center. You don't have to overcompensate low for high and high for low. You don't have to do something different for one or the other. Both of these will naturally hit low. So if you aim low on up or down vertical angles, you should be right on target. Let's see here. And then we have transonic ballistic performance. I don't have a clue how to show this with everyday objects. I have nothing to go supersonic. And even if I did, I don't think I'd have a way to capture that. But the premise there is that, let's take another non-coffee snap cap. Bullet along its trajectory at supersonic speeds, once it dumps below supersonic, goes transonic, and then subsonic. Between hypersonic and subsonic, transonic causes disturbances in the drag around the projectile. So you will get a nice spinning projectile, and then once it goes below sonic, it will actually have a disturbance in flight until it resettles back into subsonic flight. That transitionary period can cause either keyholing, because your bullet is not perfectly perpendicular to your trajectory. It could cause some aerodynamic issues because you've got more surface area working against your ballistic coefficient. It can cause some issues. It might not cause any issues. The transonic portion of flight is very slight. To have terminal ballistics affected by that would be hard to plan, if not impossible. And that's it. Thanks for your time
tonight. For my bibliography information, I did use for, let's see here, gyroscopic drift, Applied Ballistics. I used their article, appliedballistics.com, gyroscopic drift and Coriolis effect. For the Magnus effect, I did use the Magnus effect Wikipedia article. Coriolis effect, I used the Coriolis effect Wikipedia article. And then Transonic, I actually used a video, an article from Precision Rifling blog, Extreme Long Range Tips 3 Ballistic and Time of Flight Precision Rifling blog. They talked about time of transonic flight. Thank you, and have a good evening.